Hello, my name is Nicole Ten. This is a pre-recorded presentation for the 2020 meeting of the Society for Mathematical Psychology. Today I'll be talking about applying Bayesian hierarchical modeling to understand anxiety and belief updating using the classic BEATS task. The classic BEATS task is a probabilistic reasoning task whereby participants observe as many bits as they wish and decide the source of bits being drawn, either from jar A or jar B. The sequence of bits participants receive is usually predetermined. There have been a few variants of bits ratio in the literature, as shown in this table. The tendency to decide after observing two or fewer bits is known as the jumping to conclusion bias. Some researchers have observed this bias in clinically anxious individuals, but the findings are inconsistent. Relatively low decision threshold and overweighting of evidence can contribute to this bias. As these variables are often difficult to be measured explicitly, they remain relatively unexplored in the anxiety population. Therefore, the goal of this study is to propose a model of belief updating which focuses on the influence of anxiety on evidence weights. We propose two versions of the Bayesian graphical model. The first version is the simpler probability judgment model, whereby participants report their perceived probability that a given bit sequence comes from one jar versus the other. The bits with the color that appears most frequently in a given sequence will be referred to as the dominant bits. In our models, we also make assumptions about some underlying distributions and acknowledge that there are other distributions that may better describe the parameters. Suppose evidence weights are computed following the formula here. The major component is the influence of anxiety, which we assume to follow a normal distribution. The average evidence weights for the dominant and secondary bits, as notated by AD and AS, are assumed to follow a log normal distribution with a mean of 1. This implies that at the population level, on average, individuals have equal weighting for all bits observed. Any deviations of evidence weights from the population level come from the influence of anxiety. Evidence weights will influence participants' probability judgment through their prior and posterior beliefs. In our model, posterior beliefs follow a contemporary version of the Bayes theorem. The final observed note is participants' reported probability judgment as notated by PR. PR is assumed to follow a normal distribution with a mean of normalized posterior beliefs about the source of bits and a precision parameter. The second version is an extended model. Instead of reporting perceived probability, participants would report their binary decision about the source of bits. Participants' posterior beliefs contribute to the accumulation of evidence, which is assumed to be the log likelihood ratio that the bits come from one jar rather than the other. For example, when the accumulated evidence for jar A at its participants' threshold, which is controlled at the log of base factor of 3, participants would decide that the observed bits come from jar A. The same logic applies to jar B. So we first explored the properties of our models via a recovery study using simulated data. The results that I will be showing shortly are from the probability judgment model. Our simulation included 25 agents who undertook 4 different bits ratio as shown in the table earlier. We also included increasing error rates in agents' probability judgment. Key parameters for recovery are evidence weights and the influence of anxiety on evidence weights. Estimations were performed in JAX. We ran Markov chain Monte Carlo two-chain processes. For each chain, we drew 12,000 representative samples from the posterior distributions with the first 2,000 steps discarded. The results here are based on a thin sample of 2,000 averaged over 2 chains. Here, we can see that convergence is skewed across all error rates with a maximum R-hat value of below 1.1. There is a linear relationship between the known and estimated evidence weights for both dominant and secondary bits across all error rates. This means that the model is able to estimate the smallest evidence weight for the agents with the smallest known evidence weight, and keeping the trend across all agents and across all error rates as well. Moving forward from here, further simulation studies can be done with various conditions to assess accuracy of estimations in both models. Then, these models can be applied to real experimental data to understand how anxious individuals assign evidence weights, and therefore how that will influence their decisions. This will also allow us to compare the deviations in evidence weights from rationality in individuals with high and low anxiety. That is the end, and thank you for listening.